Hi, welcome to the Calculus 3 lecture series. And we are in the unit Vector Calculus. And this is our lecture number 8 for this unit here. So in this video, we're going to talk about how to parametrize a surface. The reason why we talk about this topic is because we are doing the preparation job for our next topic. So our next topic will be how to do the surface integrations of the vector field. And when we start this unit, we start doing the line integration of the fields here, right? So now we kind of expanded that. We're going to take a look, how can we do the surface integration over vector field? And so the first thing we need to do is we need to know how do we define the surface? How do we parameterize the surfaces here? Okay, so now let's go to our lecture notes here. And okay, before we start, let's kind of try to remember what we did previous, when we do the line integrals, right? So what do we do? What do we find here? We want to find a parametric out here. We want the parametric for the curve, right? So because we do the line integral, so we need to know how to parameterize a curve. So we did for example, see here, so you will say, how do we parameterize it? You can say that x is here, right? It's equal to a function of t, and then y is a function of t, see here. Then the t is vary from certain range, certain intervals here from the A to B here, right? So for example, we know how to do some very easy ones here. So for example, if I want to do circles, right? So if I say, hey, this is my circle with radius is 2. Okay, so for these ones here, then we can say we can parameterize, we can say the x is equal to what? We can say it's 2 cosine t, and then we can y, okay, I'm sorry, it's the square root of the, no, it's a 2, right? So the radius is 2, here's not the square root of the 2, right? Okay, so we put it here, so we said x is a 2 cosine t, and y is a 2 sine t here, right? So then we said t is from 0 to what? To 2 pi. So that is how do we parameterize the curve, see here, right? So when t equal to 0, you will have 1 and 0. That means you're starting this point. So when the t is to increase, change value. So that's how you start to form these curves here. So this is what we say the parametric curves, right? So how do we find that? So for other examples here, we can set up, we say, hey, y is equal to the x squared, it's a parabola. So how do we do that? Okay, so if we set a parabola, the only parabola we are interested in is here, this curve is here, right? So it's 2, then here it's 4. Okay, so the things we are interested, if we want to integrate over here, so we are interested is in this curve. So we say, yeah, we can parameterize that. So how do we say? We say, okay, let's just do the x equal to t, then y equal to what? T squares, right? So we'll say the t is from 0 to what? 0 to 2. Let's represent this curve here. So now we were going to expand that into 2 dimensions. Here are 2, D2, because we right now, instead of curves, right, we need to parameterize. We need to have a parametric what? Surface. Okay, so now naturally, when you have a curve, you have 1 variables, right? T here. So you vary the t in the curve form. So for a parametric curve, so you will be able to say, okay, now I'm going to have 2 variables here, right? So the 2 variables here, you will have like x equal to, so instead of just depends on the t, then we said x is a function of u and v, y is equal to a function u and v, and if you have a z, z can be equal to a function u and v, see here, right? So for a given value of then, of course, then you need to have the interval for u, and maybe you have the interval for the v's here, right? So like v's here, c to d, then you know you can form a surfaces here. That's what we call this parametrize a surface. And so we want to do the surface integrations, just like we want to do the line integrations. So we want to change the integration, like in the line integrations, right? So when we say here, like if you want to go over this curve, right, f of dr, so what do we say? We say, hey, you want to change, use the parametrics in here. So you change this integration to what? To one single variable t integration. Then you can use your calculus 2 idea, try to solve it. So here is the same. I hope that when I do the surface integration, I can simplify it to become to the integration form we are familiar with. Okay, so that's what we talk about is parametric surfaces here. So let's take a look here. Okay, so that means in here, right? So you have R is now it's vector UV. So in here, take a look here. So that's why we say X is a function of the UV, Y is a function of the UV, and Z is a function of the UV. So this is a vector functions here. So in defining UV plane, just like we do the line integration, we define a curve, x equal to function t, y equal to function t, z equal to function t, see here. Okay, so this is what we call this parametrize the surfaces here. So for examples here, this is give you an example. So if you say, okay, so here, this is how do I say it? I said, okay, so here, this is my x, this is my y, this is my z, right? So that means I have this is x, this is y, this is the z here. Okay, so that means, you know, x is a function of uv, y is a function of uv, z is a function of the uv. So like in here, if, you know, from this, right, so from here, from, oh, okay, sorry here, I don't know why. Okay, so from here, right, so the, here, let me say here, from this, for every u and the v, just like we did it before, when we do the t's here, right? So right now you still have an area. So for here, then you can say here, all right, so if 0, 0, right? So if 0, 0, 0, 0, 0, right? 0, 0, then this is a 6. So 0, 0, you know, you transfer to a 6 here, right? So this is a 0, 0. Did you see the corresponding here? 0, 0. Okay, so the same way here is 1, 0, right? 1, 0 is you transfer to this number 3, 0, 0 because you plug that 2. That is how, so the resulting surfaces here, right? So this is the resulting surface. This is the surface, you know, we create by using this parametric settings here. Okay, that's what we say is parametrize surfaces here. Okay, okay, so the next things here, so we said we introduce a new terms here, and these terms here, we call this is the grid curve, right? So we talk about this is the grid curve here. So this grid curve is basically, that means if you fix the one variable, so like in here, if you fix the mu 0, then if the fixed mu, that means u is a constant. Then so you only, now you parametrize become like what we did for the for the line integral, then you are parametrize lines here, right? So then this line we call this grid curves here. So like you can see here, right? So like when u is equal to 1/3, then you parametrize this line, so it's kind of like here, all right? That's how do we say is parametrize the surfaces here, because we do need this later to try to take the integration, the integration by surface, okay, surface integration. Okay, so now let's take a look at this one. So this is the surface here. Let's take a look here. So this surface here is a cone, right? So this is the cone, is z squared equal to x squared plus y squared here, okay? And I want to parametrize these surfaces here. Okay, so now, like if I say this is the regions, right, in the r theta plane. So I can use here, I can say the theta is from 0 to what? Is 2 pi. Then what is my r's here? R is from 0 to 1 here, right? So now I can parametrize it. I can say x equal to what? X equal to the r cosine theta. And the y equal to the r sine theta, all right? And then the z is here, right? Z is equal to what? Z equal to the r's here. So this is, see here, we transfer the x, y, z. Right now, we transfer to the r and the theta. So we need to use 2 parameters to parametrize this cone here. Right, so far so good. Okay, so now the next one here is, this one's not quite easy to visualize that. So from x equal to, from x from 0 to 2, you have functions here, y is equal to x squared, okay? So the y equal to x squared, and then you are rotating about the x-axis. I want to find the surface of the revolution by revolving y equal to the x squared, okay? So in here, okay, so like I said, just like when we did a line integral, the hardest one is to try to find these parametric equations here. Okay, so for these ones here, well, let's say here, I said the x here, right? So the x here, I can parametrize this way. So I can say that, hey, the x is what? I just said x equal to x itself. Oh, let's not confusing like that. Okay, so now let's take a look. I said x equal to t here. Okay, so if x equal to t, then y, okay, so because I'm trying to parametrize the what? The surfaces. So when you're rotating, right, along the x-axis, so the surface, okay, so we know when you're rotating here, the surface here is a what? It's a circle, okay? And so with radius, is equal to the x squares here. Okay, so here, let me go to the next page and let me try to do a better graph showing you. It's a little bit bigger graph, so you'll be able to see better here. Okay, so now let's take a look at this one, see here, all right? Okay, so in here, if this is the z, this is the y, and this is x here. Okay, so this is x, y, z. Okay, so now if I have some x function and I am like rotating here, right? So, okay, so I'm rotating here. Okay, so you have some type of the function, and then you are rotating around the x-axis, right? So that's why the first things we say, okay, so that's why the first things we say, the rotating. So the surface is what? Each surface is the circles, right? Okay, so now let's take a look. right? So in here, so like if for given, okay, so let me see here, let's see here. If you give me any x here, for any given x here, right? Okay, so now you want to find z, so z is here, right? So it's the top, that's what is z is here. Then you're going down, let's here, so here. Right, so this distance is what? This distance is y, right? So this distance is y. So for any given x here, this distance is y. And then here, this is my angles here, right? So this is the angle formed, it's theta. And so this distance here is what? Is z, right? So this is the any points on the surface here. This is x, y, z here. Do you see here? So if you set x equal to x here, right? So x equals, so x given a special value of x is here. So what is the y values here? So the y will just be what? Y is adjacent, right? So it's whatever this function is. So we know the y will be what is adjacent. So it's f of x cosine theta. Then what is z here? The z is the same things, right? So it's whatever the function is, and then now it's the opposite sign. So z is f of x sine theta here. Did you get that? Okay, so now you go back to our previous. So now I know because of the y, the y equal to the x squared, that means the f of x is equal to the x squared, right? So now that's why I can say here, I will say that, okay, this is how I'm going to parametricize this curve, this surface here. So the way we parametrize, this is y is equal to what? It's f of x. So x is t, so it's t squared what? Cosine what? Cosine theta. Then z is equal to what? T squared sine theta. So this is, so you transfer to the two parameters. So one is t, other is theta. So that's how we use these two parameters to parametrize our surfaces here. Did you see that? Okay, so as I said, this one is, you need to kind of draw that out so you'll be able to visualize that. Okay, so now we know how to find how to find the equations, how do we parametrize surfaces. Sometimes I say it's not quite easy here. Okay, so then the next things we want to talk about. Okay, so we know that we learned this before. So we said that the tangent plane. Okay, so if you give me a specific point x0, y0 on the surface, then this surface was parametrized by the RUV. So the tangent plane to this surface at this point, right? So we know that means the RU cross RV. So what that will be, it will produce a perpendicular vector. So that's a cross product. So that one, because it's a perpendicular vector, that is uniquely determinant of planes, right? So we learn in the like a few units back, we talk about the geometric space. So we know the normal vector is uniquely determined the plane. So because we can find it, so the RU-RV cross product is the normal vector. So that what is our tangent plane will be, looks like, so will be this is the normal vector and the dot, you minus the points here, okay? So we say the surface S is smooth if the normal vector is not zeros here, okay? So that's why, then that means you'll be able to find the tangent planes here. All right, okay, so now let's take a look at the problem number 3 here. So the problem number 3 will tell us S is a surface in the 3 dimension. X equal to U, Y equal to U squared plus V squared, Z is equal to V. So as you can see, this surfaces here was parameterized by these two variables here. I want to find the normal vector and the equation of the tangent plane at this point. Okay, so now let's take a look here. So first here we know the RUVs, right? So it's the X, so we say it's XI plus YJ plus KZKs, right? So I know the RUV, so this one's here will be the U, and then this is the U square plus V square, and the, sorry, there's no plus anymore, right? Oops, try to erase it. Okay, so now the U square plus V square and the V's here, right? So I know the normal vector is the cross product of the partial for the RU. Okay, RU and RV. So I take the partial derivative of RU. Let's take a look. That means I'm taking the derivative of U. So it's 1, 2U, and what? And the zeros, right? Okay. Then the RV, that means I'm taking the partial derivative for V. So this is 0, 2V, and the 1, right? So the now, after I do that, then I know my normal vector is the RU cross RV. So we can use our cross product definition. We put the IJKs here. We put the RU is 1, 2U, 0, RV is 0, 2V1, right? So you can use the same technique like we did. So you put the IJ out. So this is 0, 2U, 2V. Then you do the cross product, right? And then the minus the, like you do like we did many times. I'm not going to, spend more times here. You do this, then you minus, you go this way, right? Okay, so now after you do that, so we know the cross product of RU minus RV. So I assume you know how to do this. So this will be 2U I minus J and plus 2VK. Okay, so this is my normal vector. All right. So now at the point 1, 5, 2 here, right? So at the point 1, 5, 2, okay, the point 1, 5, 2, that means, what's that means here? That means this is my X value, this is my Y value, this is my Z values, right? So then I can say that this point, my X is equal to U, so U is what? So I'm going to have U is equal to 1, then V, okay, Z equal to V, so V equal to 2. Let's check to see Y is the same or not. So Y is U squared plus V squared is 5. Okay, that's perfect. All right, so I know, so after that, right now you can substitute it here. Okay, because after you find the U and the V, you can substitute to your normal vector. So now I can find my normal vector will just be, you substitute the U equal to 1, 2U, so this is 2, and minus 1, and last is here, V equal to 2. So V equal to 2 is 2 times 2 is 4, right? So my normal vector is 2, negative 1, the 4th here. So after that, I know it is uniquely defined by normal vector. So I know my tangent plane, okay? So you still remember what is that? So you use your normal vector constants, right? So you will say 2. Now which one is passing? X minus 1 minus, because minus 1, minus Y what? Minus 5. Then plus 4 times Z minus what? Z minus 2. Okay, equal to 0. If you want to simplify it a little bit, and then you can say this one is the 2x minus y plus 4z equal to 5. Okay, So this is the, so this is the tangent plane to the surfaces here, okay? And also, because my normal vector, this is not a zero vector, so I know the surface is what? Surface is smooth at this point, right? Okay. Okay, so far so good. All right. Okay, so now let's take a look at the other ones here, right? So the other ones here, they say, let the equation of the plane tangent to the surface at uv equal to 1, 1, where s is parameterized by, the x equal to the 2u squared v, y equal to u plus 2v, and z equal to the 2u plus v here. Okay, so now let's take a look here. So I know the RUV is equal to the XI plus YJ plus ZK, right? Okay, so now this one's here. So my RUV, what is RUV here? What is this vector? Is 2u squared v squared, u plus 2v, then 2u plus v. Correct. Okay. Now let's take a look at our partial derivative of the u. So partial derivative of the u, the first term will become what? 4uv. What is the second term here? It's 1, right? What is the third term here? Is 2. Okay. So the same thing, I take the partial derivative for v. So what is the derivative for here is 4u squared v. I think that this one is 4u, this should be v squared, so I need to be careful. Okay, so this is 4u squared v. Then take the derivative of the v, this is 2. Take the derivative of the v, this is 1, right? Okay, so now I can find my normal vector. So the normal vector will be RU cross RV. So it's the same way you use the determinant methods here, right? So here, then put RU in here. This is 4UV squared 1, 2. Right, then put RVs here. This is 4U squared V 2, 1 here. Then you do the cross product. I assume you know how to do the cross product here. So the final answer for this one is 3i, okay, plus AU squared V minus 4uv squared, and this is j's, right? And then plus this one is auv squared minus 4u squared v, the case here, okay? So now, because now the UV, so right now they give us UV is equal to 1, 1. So now I can find my normal vector. You just plug 1, 1s here. So the normal vector is -3. So 1, 1. So this will be 4, right? So 1, 1. Still good. So it's 3, 4, 4 here. Right? So for the 3, 4, 4, now I plug in the xy's also, because this is equal to x, this is equal to y, this is equal to z. So I substitute 1, 1. So 1, 1, this will give me what? It's 2. 1, 1, so this give me 3. 1, 1, this give me 3. Okay, so now from here, I can say my xyz equal to what? 2, 3, 3, right? So now I have a point and I have a normal vector. So what is the tangent plane? That's what we learned in the previous units. So the tangent plane will be used the normal vector. So it's -3 x minus 2 plus 4 y minus 3 plus 4 z minus 3 equal to 0, right? So if you want to simplify, combined, you will get this is 3x minus 4y minus 4z equal to the negative 18. So this will be my tangent planes here, okay? All right, so now this is the how do we parametrize a surface. And as you can see, it's basically is almost the same as you parametrize a line. So a line, you have not a line, we call it a curve. You have one variables, right? So right now, in order to parametrize a surface, you have two variables here. And then in order to find the tangent plane, so you can, so then the partial of the RU, partial of RV, when you cross product will give you the normal vector. That's then with normal vector, then the tangent plane is uniquely defined. Okay, that's it. And then next units, we're going to use what we learned from this unit and try to do, we call this a surface integration. And in the physics, we have a very specific application for that is we call this the flux. All right, that's it. And looking forward to talk to you in our next units. Okay, all right, bye.